Alright, so in previous videos, we've talked about just an inductor and a capacitor in series in a circuit, and that's it, right? There was not a voltage source. Now let's introduce a sinusoidally varying the voltage source, right? This means that the oscillations in the circuit will be driven or forced, okay? And a simple way that you can do that is the voltage source can be, well, pretty much that loop, right? That wire loop in an external magnetic field, like that, right? So that's rotating. That loop there is rotating around and around, creating an AC current, right? An alternating current. And so these leads are somehow connected to, in this case, we'll start out with just a resistor, right? And so that's why this is known as a resistive load, okay? So these oscillations and the current are being driven around the circuit and thus across that resistor. So there's only two circuit elements, okay? There's the EMF of the voltage source, right? So this effectively is one giant, the battery, E. So we have that, and then minus the voltage drop across the resistor, which for now I'll just write as V of R, right? And that's it. So that's a very simple Kirchhoffs loop rule for this resistive load circuit, all right? And so ultimately, in this video and the next two videos on capacitive and inductive loads, the goal will be to compare the voltage across the circuit element, resistor, inductor, or capacitor, compare the voltage drop with the current, right? Compare how they are acting, right? And it turns out that they'll change depending upon which circuit element we're dealing with, okay? So for right now, this is what we have, so let's see what happens. This means that the EMF is equal to the voltage drop across the resistor, right? So that's pretty straightforward. The sinusoidal EMF produces a sinusoidal voltage that can be written like that, right? It has some initial EMF times some sine of omega t. And this, by the way, is the driving frequency, the driving angular frequency. Right? Omega sub d. That's the frequency with which this current loop is being rotated, right? Creating a frequency of current oscillations back and forth around that circuit. Okay, it's not the natural frequency like we've studied in previous videos. That's just written as omega, right? That's just omega, which was, by the way, 1 over square root of LC. Well, in this case, we don't have an inductor or a capacitor, so we just have to have omega d, right? And then T, of course, is time. So that has to equal the voltage drop across the resistor, which I'll keep as V sub R, but I know it's just IR. However, the voltage drop across the resistor is also dependent upon the frequency that the current loop is rotating, right? It's dependent upon the sinusoidal EMF. So we have to include that term in the voltage for the resistor on this right side of the equation. Okay, so this is the maximum voltage, right? It's simply IR, but we have to include this sinusoidal dependency on that, okay? And so that means that both the EMF and the voltage drop across the resistor are dependent upon that driving frequency, right? And so we want to compare this voltage. So let's see, let's mark that equation 1. This is the, let's see, voltage across resistor. We want to compare this with the current through the resistor. Okay, so keep that equation 1 right there. Now, let's look at the current. The general, sorry, let's write it like this. In general, that's right, general formula for a current with a sinusoidal EMF. General formula for, I'll write it as I of t, okay? Since this voltage source is varying sinusoidally, that current also varies sinusoidally, right? Thanks to Ohm's law. And so the general formula for that, I'll write it as I of t, is equal to some initial current times sine of omega t, and then we also have to include some phase constant, because we'll see that the current using this general formula and the voltage across whatever circuit element we're dealing with will not always line up. They'll not always be in phase. So to compensate for that, we have to include this general phase constant, phi. Okay. By the way, phi is written like that. It's Greek letter. It's not necessarily theta. It's a different angle, but phi. Okay. And by the way, it's a negative right there. It's a negative purely by convention, right? Just by a convention. Just like the current is effectively, from plus to minus, when in reality the charges are going from negative to plus. That's a convention. This is another convention. So just, roll with it. Okay, so using this general formula for the current, let's see how the current behaves for a resistor, right, or across that resistor. So the current across the resistor as a function of time, well, is simply that initial current, which has to vary exactly with whatever EMF is being provided, right? We said this was the voltage. Well, the current is directly related to that voltage right here. So in fact, we can rewrite that a little bit if we want to. Current, let's see, V equals IR. So current is V over R, right? And I'll write that as voltage of the resistor. Now, we should notice that this current through the resistor also has a sine of omega t, just like the voltage did, sine omega t. That's because both the voltage and the current across this resistor exactly depend at which the rate, or on which the rate at this loop rotates, right? And so thus we have to include that in there. There is no phase constant. There is no phase constant because they both depend exactly on omega, and the current depends on the voltage. So phi is 0. Okay? And if phi is 0, that means they're exactly in phase. And if we were to draw a graph of those in time, so this is graphing both voltage and current on the y-axis, it would look something like this. I'm just going to draw a hypothetical sinusoidally varying voltage. Right, there's some maximum VR, and the current hypothetically can go up here. Something like that. Notice they're exactly in phase. Right? And so the maximum are V and R, or V and I, sorry. They're in phase because both this sine argument there and there are exactly the same. There is no phi. And by the way, after one complete cycle, the time to complete one complete cycle is 1 period, the capital T. And the time to complete 1/2 cycle is half a period, so T over 2. Okay? So as these plots, right, move either way, it doesn't matter, left or right, they will remain in phase because they're both dependent upon the same frequency. You may, or you can write these as phasors. Excuse me. Phasors, let's do in blue, let's write for the voltage. Let's do it like this. So at some angle, it doesn't matter. It's just for illustrative purposes, V of R is right there. And I'm going to choose red for current. Right there. So they're in the same phase because they are at the exact same angle. And by the way, if they're rotating this way, counterclockwise, at the frequency omega d, that means they'll pass, well, this location, right, pi over 2, at the same time. They'll pass every other angle at the exact same time because they are, again, in phase. And the angle between them then is 0. By the way, look at their sine components. Right? They're sine components of this angle here. When they are at pi over 2, right? When V of R is at pi over 2, it should look something like this. It's up there. And that should be the amplitude of the graph over here. It's not quite to scale, apparently. But this height should be the same when that blue phasor is crossing pi over 2. Same thing for the current. When this red current phasor comes up here and crosses pi over 2, that height should be the same as the amplitude of its plot over here. Okay. All right, so this was a purely resistive load for a sinusoidally varying voltage source. Keep these, I guess, these methods in mind for a capacitor and inductor. Again, we want to compare the voltage to the current through each of these elements. Okay, so for a resistor, they are exactly in phase and phi equals 0. Thanks for watching.